nanohub.org.
Online simulation and more for nanotechnology.
Hello everyone, it's been a pleasure for me to give this presentation, this seminar here, and especially contribute to the NanoHub website. I'm going to present you here some results in a technique widely used in a lot of fields called impedance spectroscopy. I will start with a brief introduction to thermoelectric materials, and then I'll show you what are the fundamentals of this technique, this method. Then I'll show you the theoretical background required to understand the measurements. Finally, I'll present some experimental validation for those theoretical models. I will look a little bit in detail to some physical meaning of the parameters extracted from the technique. And finally, I'll acknowledge some people who contributed to this work. So most of the energy produced in our society nowadays is lost as heat. For example, in two applications, the electrical consumption in our houses from power plants, around 60% is lost as heat during generation, and around 10–15% in transport and transformation. This is a total of around 70% losses in waste heat. In cars, in transportation, around 40% of the energy generated is lost, and 30% is used to cool the engine. It's again a total of around 70% losses, plus the consequent CO2 emissions. So the main characteristic of thermoelectric is they have the ability to convert temperature difference directly into electricity. So you can obtain electricity, obtain power from waste heat. So the role they can play in the current energy system is contribute to improve the efficiency of the energy. There are a few applications because there are wide range, because there is waste heat released in a lot of areas. For example, in furnaces, they are very high temperature, heat is released. Also, you can take advantage of the fluctuations in temperatures in the ambient, and you can power very small devices which require very in the microwatts power. Also, this is very classical application in the aerospace. There is also a thermoelectric solar cell where you convert the light from the sun into heat with a solar collector and then use this heat to harvest energy. I think it's around 4% this solar cell efficiency. And finally, maybe the most spread or currently the most powerful application pushing the field forward is the application into the exhaust gases, which are released at high temperature. This in order to improve the consumption and the CO2 emissions in cars. So how do we calculate the efficiency of thermoelectric materials? The efficiency is the maximum power divided by the input heat. Under a few assumptions, you reach to this equation. If you have a look to it, there is temperature difference involved between the hot and cold sides, and also there is a parameter here called ZT, or the figure merit. So ZT gives us an information of how efficient is a thermoelectric material. But don't forget always, it's very important that apart from ZT, we need to provide the maximum delta T as possible. In the ZT, we have three parameters apart from the temperature. We have the Seebeck coefficient, which is the voltage at open circuit that is generated under certain temperature difference. We have the electrical conductivity of the material, and finally the thermal conductivity. You can get a high high ZT if you have a high Seebeck coefficient, so provides higher open circuit voltage. If you have good electrical conductivity, so provides higher current, or if you have low thermal conductivities, which provides higher temperature difference. One of the more higher difficulties in this field is that all these parameters are interrelated. So it's very difficult to modify one of them without altering the others. And when you improve one of them, the other get worse. So it's very hard to research in thermoelectric and get good materials because of this trade-off. There is a wide range of materials in thermoelectrics. There are typically highly doped semiconductors. There are silicides, there are escoteriodides, oxides, silicon germanium, bismuth telluride, which is the most standard compound and the one which is currently on the market. And also conducting polymers have recently shown some attractive properties. There is a list of the different materials against ZT and the temperature range where they usually operate. Characterizing materials is not an easy task. It's quite tedious because we need to provide the evolution with temperature of 3 parameters: the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. Usually 3 different equipments are required, and also there's a wide variety of homemade techniques, and usually research doesn't follow standard methodologies. And finally, the efficiency, the ZT, is usually obtained from the measurements of 3 parameters, and it collects the errors of all of these parameters. And finally, thermal conductivity is the most difficult property to measure because it involves heat fluxes that escape anywhere. It's not like currents, they are always in the wire. Heat skips everywhere, it's difficult to measure. Here there are 2 pictures of homemade techniques. This is the hot probe we have at Cardiff University, and this is a 4 probe for electrical resistivity. This is your sample, and there are 4 probes contacting. You apply currents and voltage, and you get the electrical resistivity. In the next section, I'm going to explain you what are the fundamentals of impedance spectroscopy, the technique I'm going to show you some results. In impedance spectroscopy, we apply a small sinusoidal voltage. It can be also a current, like this, with a small amplitude. It's important to keep a small amplitude because we want a proportional relation with the current. So once we apply this sinusoidal voltage, the system responds with a current, with another certain amplitude, and also it can be shifted in time, so you have a phase there. Once we run this experiment at a given frequency, we can plot the result into the complex plane. So we have a point which is given by the modulus, which is provided by the ratio between the AC amplitudes, and the angle of this vector is the phase. You can get the angle from the tangent. If we do this experiment in a range of frequencies, we get the impedance spectrum. Usually high frequencies appear on the left side, then you start to decrease the frequencies, and you end up at the right side. So each of these points is one of the frequencies we've done our experiments. Usually, apart from the complex plot or the Nyquist plot, you also can show the results in both the plots as a function of frequency. You can plot the phase, the imaginary, the real, the magnitude. There are some parameters that when represented in the frequency axis, they are called Bode plots.
What is the device on the left-hand side?
I don't know, it's kind of book. It's a picture from a book. It's not related with any device. These are resistance in series with a capacitor. I'll show you something. The way we interpret the results in impedance spectroscopy is using equivalent circuit. So for example, if we take a resistor, we connect it to the impedance analyzer and we perform the impedance spectrum, we will see a point in the value of this resistor, in this case 100. The magnitude is constant with frequency and there is no phase shift. If we connect our resistors in series with a capacitor, the spectrum changes. We have now a vertical line going from 0 imaginary part at high frequencies and then to infinite at very low frequencies. And also the body plots change as well. Another example is with classical semicircles. When you have a resistors in series with a parallel combination of resistor and capacitor, you see a semicircle which is shifted in the real axis, the value of the series resistance. There are also parameters like the frequency at the maximum point of the semicircle, which relates with the capacitance and the other resistor. So in principle, from spectrum and performing this equivalent circuit fitting, you can get the properties of your materials. Here you can quantify the resistors, the capacitance. This technique has been widely used in a lot of fields, in solar cells, batteries, fuel cells, supercapacitors, corrosion is very powerful. One of the main points of this technique, it allows the separation and direct determination of the different processes occurring in the devices. And also it can provide results at operating conditions. This is an experimental measurement, impedance spectrum of a dye-sensitized solar cell. For example, here you can see the intercept. There it provides the ohmic contribution of the cell, which is the wires plus contact resistance. Then you have a one-slope trend, which relates with electrical conductivity in your nanoporous material. Then you have a semicircle, which relates to the recombination in the solar cell. And finally, you have kind of overlapped semicircle, which gives information about the diffusion of ions in the electrochemical solar cell. So as you can see, again, from our impedance spectrum, we can quantify a lot of properties from our system. We can quantify Hall transport, electron, lifetime recombinations, diffusion of ions.
So I guess the solar cell is a nonlinear device. But you use such a small amplitude that you don't have to worry about?
No.
So what is the amplitude typically?
Typically it's 10 millivolts, 10, 20 millivolts, 50 maximum.
You said you should use the same amplitude in thermoelectrics, then can you create the delta T that you want because you need to maintain a delta T?
Yes, in principle, you need a small amplitude because you want a proportionality between your voltage and your current. So you can apply all the formulation in the impedance. In thermoelectrics, I usually apply 20 milliamps root mean square, and this is enough to see results and also to stay in this region of proportionality. Okay. So you need to experimentally select your amplitude when you perform the measurements. Impedance spectroscopy has hardly been explored in thermoelectrics. There are two groups which, especially Downey et al., they did some studies a few years ago, and they related the equivalent circuit in the electrical impedance with the thermal equivalent. So they reported a resistance and capacitance in parallel, which is the main feature of the thermoelectric response. And they related these parameters with the thermal capacitance and the thermal resistance of the module. The other group, which has been done some work on impedance, is in Italy, and is led by Gareto et al. And they provided the physical and mathematical description in the context of a thermal impedance. Thermal impedance is, instead of tracking the relation between voltage and current, we track the relation between the heat flux and the temperature. They published few papers. These are the two main ones. And they also developed a method to accurately measure the ZT in thermoelectric modules, thermoelectric devices. So the literature reported so far is mainly focused on the calculation of ZT. And despite of these studies I've mentioned, is nearly not used in thermoelectric. If you search in the literature, you will probably find only 2 articles using this method. And I believe is a very powerful technique, which, for example, in a lot of fields has been used to provide very useful information. So I decided to explore a little bit further this technique in thermoelectrics. So in this seminar, I'll present you some of the results we have achieved so far, especially the development of the theoretical methods in the context of the electrical impedance, not only as a thermal impedance. Also the analysis in the complex plane, which is the more sensible way of analyzing impedance results. And then I'll show you how we can exploit the impedance results to provide complete characterization of thermoelectric materials, and also to quantify the losses of the system. Let's go to the theoretical background. There are a few assumptions in the model. The thermoelectric element, we will consider a thermoelectric element with a certain area and a certain length, contacted by two metallic contacts, usually copper. I will assume adiabatic conditions all in the surroundings, so there's no heat exchange. Also, all the thermoelectric parameters are not dependent on temperature. And I'll assume the system is initially at equilibrium at the temperature in Ti, and then I'll neglect the Joule effect. This is possible because I'm using a very small AC amplitude, so the delta T applied across the thermal element is very small, and convection can be neglected even if there's no vacuum. And also thermoelectric materials are very highly conductive, and under small currents, Joule effect is not so relevant. We also apply these equivalencies. So I will consider a temperature difference, which is the temperature distance to the initial, the temperature versus the initial equilibrium. So the derivative of this temperature difference equals to dt. Here the blue line indicates in an n-type thermal element at a certain moment in time the temperature profile when we apply a positive current.
So I guess you just drew the temperatures by hand, but if it's adiabatic, the temperature cannot have a slope coming to the end, correct?
Yes, it's a scheme, yeah. So what is the impedance function? The impedance function in the time domain is the ratio between the voltage and the current. In thermoelectric materials we have two voltage drops. One is given by the ohmic contact, this is related with the electrical resistance of the material, and also contact resistances and wires. And then we have the Seebeck voltage drop, which is given by the Seebeck coefficient and the temperature difference. So our impedance in the time domain using these voltage drops becomes this equation. Impedance.
Temperatures are also a function of current, correct?
Yes.
So why don't you put it inside?
Because later on they will cancel out because of the Peltier effect. In order to transfer to the frequency domain, impedance works as AC method. I need to apply the Laplace transform. So I define theta as the Laplace transform of the temperature difference versus the initial equilibrium, and the Laplace transform of the current as I, and then the temperature difference between hot and cold sides at 0 and L is equals to minus twice the temperature difference at 0. So when I go to the frequency domain, I have this equation. So to know the impedance function, we need to know the temperature difference at 0 as a function of frequency. Because the system is symmetrical, the total temperature difference is twice as I've shown. So in the end, we need to solve the heat equation. I'm going to show you the solution or the manipulation of the heat equation under two approaches. The first one is the heat balance with no contact influence. We'll assume a very thin contact here. For example, if you spread a bit of silver paint, you easily get this approach. So the heat balance equations in the thermoelectric material, we have heat absorption and heat conduction in the bulk from 0 to L. And the two boundary conditions we have at 0, we have the Peltier heat generated when you pass the current, and this Peltier heat only can diffuse and be absorbed towards the material. So this is the equations at 0, and we are using adiabatic conditions. Then I'm going to consider the symmetry plane here, because at any time the temperature here doesn't change during the whole experiment. So I will work with this boundary condition, so the temperature at this plane at any time is equal to the initial temperature. This is equal to establish here a kind of heat sink. So now we have to convert again all these equations in the time domain into the frequency domain. So we do this again using the Laplace transfers of the different parameters, and then it's more or less straightforward to reach to the frequency domain equations. We need to solve these equations in the frequency domain. We use this characteristic frequency of thermal diffusion, which is given by the thermal diffusivity divided by the square of the half length. So this is equivalent to the time that the heat wave needs to travel up to the half length of the element. And using this equivalent, these are the general solutions to this heat equation. After applying the boundary conditions and doing some mathematics, I reach to this equation for the temperature change at 0. So this is the final impedance function under this approach, using that the temperature at 0 is very close to the temperature, to initial temperature. I expect very small temperature difference, and also using the equivalent between the Peltier effect and the Seebeck effect. So if we plot the results for a bismuth telluride element with this dimension, this is the simulation. So this is the impedance function of a thermoelectric element. Here we see that this characteristic frequency differentiates two regimes of operation. At high frequencies I have the one slope trend, which is given by this approach. So as you can see, the frequency is, the impedance function is related as square of the frequency. This provides this one slope line. And at very low frequencies, when the frequencies are much lower than this characteristic frequency, I have this approach, this simplification, and this provides the semicircle. So if we look, we can fit this response into a equivalent circuit, which is a series resistor with a Warburg element. The Warburg is an element widely used in electrochemistry, and it's quite frequently involved in diffusion. So if we fit, imagine this is an experimental experiment, if we fit the spectrum with this equivalent circuit, we obtain three parameters. We obtain the series resistance, which provides information about the electrical resistance of my leg, my thermoelement in this case, plus the contact resistances. And then the diameter of this kind of semicircle Warburg is given by this equation. This has unit of ohms, and we call this thermoelectric resistance. If you look at it, is the ZT the figure of merit without the electrical conductivity contribution, and taking into account also the geometry of your leg. And then from the characteristic frequency provided directly from the fitting, we can identify the thermal diffusivity in our leg. So in principle, by doing an impedance spectrum, impedance experiment, we can provide all the thermal constants if we know the Seebeck coefficient. If we input here the Seebeck coefficient, we can calculate thermal conductivity. Thermal diffusivity is directly given by the characteristic frequency, and then if you have these two, you have your specific heat. Let's look now at a second approach. So now we are going to take into account the effect of the contacts. So now we have a metal strip. If we look just at this part, at the left part of the element, we now have a Peltier heat flux which can go into two directions. It can be absorbed and transported along the copper, our contact, and also as well towards our thermoelectric element. So we have these equations represent this physics. We have new boundary conditions. Now our Peltier heat is distributed into the metal and into the thermoelectric material. And at zero we have our adiabatic condition. And finally we need an extra boundary condition, which is the temperature conductivity. So the temperature has to be the same from the contact and from thermoelectric at zero. If we use all these, well, if we solve all these system of equations, we reach to the solution, which is given by this simplified equation. Here, this is a function that the temperature difference at zero is a function of the thermal impedances in the thermoelectric and also in the metal. So these are the functions of the thermal impedance which provide the whole temperature difference at zero. So finally, the impedance function is given by this equation. I'll go through this equation a bit later, so don't worry if a bit heavy at the moment. Let's now assume that the the Peltier flux generated can only travel towards the contact. So our thermoelectric material is thermal insulator. Okay? So under this assumption, thermal conductivity is zero in the thermoelectric material. We have this impedance function from the total impedance. If we plot this equation, you will see again the Warburg trend. But now, the temperature, once it reaches the boundary, which is adiabatic, it stops, and there is kind of blocking, which is given by this vertical line. So we can fit this response using our resistors in series with an adiabatic Warburg, in this case. And again, we have two regimes, the semi-infinite regime, where heat travels inside the contact, still doesn't sense the boundary. And once it senses the boundary at frequencies smaller than characteristic frequency, it gives, as you can see here, there's a fix. The real part is fixed, which is 1/3 of Rm. Rm is given by this equation. And then the frequency is inversely proportional. So if we look here at the response, we have a thermoelectric resistance which now comes from the metal, from the contact. And we have this equation. We have also the characteristic frequency. So let's look now at the whole function. Okay, so we have our thermoelectric element, our contacts, so what's the whole response of the system? This is the equation we solved previously. And now, in order to view a bit clearer what's going on, we can plot the two approaches I've used. So remember, this is the response when I only have my thermoelectric element, no contacts. And this is the response, this is a thumb here, when I have my thermoelectric element as an insulator. So if we combine both in parallel, and we connect it to a resistance, we have the whole system response, which is the blue line. Okay? So now we have a semicircle, and if we zoom at high frequency, we have this warble-like trend. And now, from this fitting,
it is a little misleading, but the units are very different because this is milliohm for the thermoelectric and microohm for the
yes, if you zoom here, to see this response, you need to go to microohms. This is because if you look at the equation here, your thermoelectric resistance from the metal is given by this equation. So the thermal conductivity in the metal is very, very high, it's around 400. So this becomes very small. And that's the reason. But if you look here, we usually know thermoelectric properties of our contacts, of copper, also from the ceramic. So if the fitting provides this thermoelectric resistance in the metal, I usually know the thermal conductivity, so we can work out from here the Seebeck coefficient of our system. And if we know the Seebeck coefficient, we can get all the thermal properties. So we can provide a complete characterization of the system. In addition, if we look at what I will get if I go to a steady state, so at very small frequencies goes to 0 around this point, you will work out this equation. So the DC resistance, which has all the contributions from the losses of your system, is given by the electrical losses plus the thermoelectric contribution. So apart from the potential of provide complete characterization of thermoelectric materials, we can also track and separate the losses of my system into the different contributions. So let's look now at the validation of these theoretical models. To validate, I've used a bismuth telluride leg, very small, usually a few millimeters square, 1.4 millimeters square area, around 1.5 millimeter length. I spread a bit of silver paint to make the contacts, and then I use 2 probes to apply the current with very sharp tips to ensure adiabatic conditions and avoid heat flux going towards the probes. And then I connect this more or less simple setup to my potentiostat or impedance analyzer. So these are the results of a bismuth telluride element. These are the geometry and the length. And you will see the response is very similar to the one predicted. And also if you use the fitting to resistance in series with a heat-sink Warburg, from the fitting you have the 3 parameters: resistance, thermoelectric resistance at the characteristic frequency of thermal diffusion. So if we know the Seebeck coefficient, if I measure, for example, the Seebeck coefficient with a hot probe method, which is around this value, I can calculate the thermal conductivity of the element, which is around 1.3. I can calculate straight away from the fitting the thermal diffusivity, and also I can calculate the specific heat. And from the resistance in series, I can calculate the electrical conductivity. In this case, it's a bit low because it also has the contributions from wires and contacts.
You can't do 4-wire measurement?
Yes, you can. The experimental setup becomes a bit more complex because you need to spot weld wires or attach 2 more probes. But in principle, the way to extract directly the electrical conductivity of your material is using a 4 probe. And then of course you can track your ZT, which is the ratio between the 2 resistances in case you remove the contribution from wires and contacts. And usually the experiment is more or less quick, it takes a few minutes, 5-10 minutes, no more. So here I have used the same thermo element, but now I have attached the typical copper ceramic contact, which you can find in any thermoelectric device. So I have this response, which is again very similar to the predicted by the models. If I run, one of the worst or most difficult things here is when you work with legs, you go to very small resistances. So we are now in the milliohm range. So in order to see the response here, we need to measure microvolts, which equipment starts to be a bit noisy and not accurate. So even if I have the response, it's very difficult to do the fitting because this part is very noisy. So in principle, at the moment, I've not managed to extract all the thermoelectric properties from here because of this. But on the other hand, I can use a thermoelectric module. The system is very similar. The only difference is if I have 244 legs. Okay? And if we use the same methodology, there are some other things to consider, but we can adopt more or less with reasonable accuracy this methodology. So the impedance function, now we need to add all the voltage contributions to each leg. So I need just to multiply 254 by the voltage, zero voltage on each leg. And then the whole impedance response is this equation. So now again I run the fitting, and now the fitting is possible, gives good accuracy, and is reproduced very nicely the experimental response. So from the fitting, I have all the parameters, and using the thermal conductivity of my ceramic from the resistance of the contact, which is this value, I can work out the Seebeck coefficient. And then now if I know the Seebeck coefficient, I can calculate thermal conductivity and also electrical conductivity, which again in the module is a bit smaller because of other contributions.
Sorry, when you did single leg Seebeck, you had to measure it separately.
Yes.
Why you can?
When you don't have contacts, the problem is your thermoelectric resistance. Here, this depends on thermal conductivity and also Seebeck. So you need to know one of them in order to work out the other. So it's not possible to provide a complete characterization because of this. I need to know one of them. For example, if I input the Seebeck, which is more or less easy to measure, I can get all thermal properties. So this is the first approach. If we want to go for complete characterization, we need to add the contact contribution. Because in the contact, the thermoelectric resistance is given again by the thermal conductivity of the contact and the Seebeck coefficient. But now thermal conductivity of the contact is well known, it's usually tabulated. So the ceramic is around 40 watts meter Kelvin. So if I input the thermal conductivity of the ceramic, I can work out the Seebeck. And once I have the Seebeck, I can provide all thermal contacts and the whole thermoelectric parameters. Let's look now at some physical meaning. There are some parameters that can be extracted from the impedance experiments that are interesting, and we're going to try to see here a little bit more physical point of view. So now we have again our thermo element, same assumptions, parameters independent of temperature, initial thermal equilibrium, but adiabatic conditions. Now I'm going to consider as well the Joule effect. So if we look at the steady state heat balance equation, the solution at the cold side is given by this equation. This is more or less very standard, frequently used equation in thermoelectrics. So now I can work out the temperature difference, and I have this expression. And from here I can calculate my Seebeck voltage, which is just the Seebeck coefficient times this temperature difference. And I have this expression. If I take this expression and I put it into the normal equation for our resistance, in this case thermoelectric resistance, which is the Seebeck voltage divided by the current, this equation results. And it matches with the impedance function at the steady state when Joule effect is neglected. If we cancel this Joule effect, we have the same thermoelectric resistance, which is given here. So what's the physical meaning of this thermoelectric resistance? At a time very close to zero, we start to apply our current, our voltage. So the carrier density is homogeneous along the thermoelectric element. And there's still no time to build a temperature difference. So the applied voltage is, the current given by the applied voltage is given by the resistance, the electrical resistance of the leg. So what happens after some seconds? Due to the Peltier effect, there's a temperature difference that starts to appear at the edges, and now the carriers redistribute and they generate the Seebeck voltage. And now the voltage we measure is the applied voltage minus the Seebeck voltage contribution. And there is a Seebeck current in the opposite direction as the drift current. So the thermoelectric resistance accounts for the losses in the system introduced by the thermoelectric effects, starting from the Peltier, which generates a delta T, and finally generates a Seebeck voltage. We have introduced as well a thermoelectric capacitance. Thermoelectric capacitance can be defined using the general definition for the Seebeck coefficient. Is just the variation of charge versus the Seebeck voltage. So current times dt, the Seebeck voltage. If we introduce the definition, we have this expression. So it relates with the speed of the temperature increase, the reciprocal. If we use the definition of the thermal diffusivity, and we insert the thermal conductivity and the specific heat from the Fourier law and the definition of the specific heat, we reach to this expression that when we input here this delta time, we come out with this thermoelectric capacitance. And finally, using the heat balance at the cold side, which is given by this expression, we have the final equation for a thermoelectric capacitance, which depends on the Seebeck coefficient and also on the specific heat. So this thermoelectric capacitance also appears in the impedance function. This is the general equation, well, this is the equation for the thermoelement of the impedance. We have our characteristic frequency, so if the thermoelectric capacitance can be worked out using these two parameters. So the physical origin of this capacitance is not well understood yet, but it gives information about the charge separation, the reorganization of the carriers, and also the process that the Seebeck current which appears in the system. It's like you discharge one thermal capacitor which provides current. And also it relates with the speed, the velocity at which the temperature difference is built. So this is a mixture of all these physical processes that can originate this thermoelectric capacitance. I'm currently trying to work out a little bit more about this parameter, and in the next European Thermoelectric Conference I will show some results on this respect. And finally, another parameter interesting is a time constant. Time constants are typical RC, so if we multiply our thermoelectric and resistance and capacitance, I reach to this equation which is related with the time that our heat wave needs to cross the whole thermoelectric material. Also, we can obtain this time constant directly from the characteristic frequency. All this physical meaning is provided in one paper we published recently, and we also showed in the last year Thermoelectric Conference in Japan. This is the reference if you are interested. So as a summary, I have shown theoretical models for electrical impedance and I've presented the analysis in the complex plane, different trends shown. Also, I have validated experimentally the models, and I've shown the potential to provide a complete characterization of the thermoelectric materials, and as well the possibility to separate and quantify all the contributions to the losses of the system. And finally, I've explored a few physical meanings, especially for thermoelectric resistance, capacitance, and the time constant that comes from the impedance analysis. There's a future work going on. This is kind of the beginning of the technique, the first models, which are quite simple. So in the future, we'll try to work to develop theoretical models for characterization under real operating conditions, taking into account Joule effect, also heat inputs, heat sinks, convection effects, etc. And then I'm working in further understanding of the thermoelectric capacitance, what's the origin, what's the meaning. And then also we are trying to look at apply this method to nanostructured materials and thin films. And finally, I would like to acknowledge my funding body who allowed me to work on this, the European Commission and the European Space Agency under the Accelerated Metallurgy project. Dr. Gaomin, my supervisor in Cardiff, for his support and contribution to this work. Also these colleagues, Bull and Matt, who allowed me to run some first initial measurements in their labs. In the beginning in Cardiff we didn't have any impedance analyzer, and they kindly allowed me to run some experiments. And finally, European Thermodynamics, a company in UK providing thermoelectric modules which supplied most of the materials used. So this is the Cardiff School of Engineering in Cardiff University in Wales, in UK. You are welcome if you want to visit us. And this is my personal website if you want to have a look. So thank you very much for your attention, and if you have any question, I'll be happy to answer.
Questions?
I would apply this method to the nanostructures. In this case, you will start having some ballistic effect coming to account, right? So in this case, applying the equation of the region like that will need to go to Boltzmann transport or something to really have this impact.
Sorry, can you repeat?
Yeah.
So if there are ballistic effects, how does it modify your analysis inside the conductor?
Ballistic effect is there's no scattering, correct?
It is thin film.
I don't have the answer yet, because
How about not thermoelectric, but just tiny, quantum barriers and everything?
Yeah.
People have applied impedance spectroscopy there?
No. There is, when you go to nanostructured materials, it's likely to appear, for example, non-ideal contacts, no ohmic contacts. You can have space charges, and they will appear as a new feature in the impedance spectrum. But I don't know which shape it could have. But in principle, I think this technique is interesting in this respect, because if you change anything, any physical process in your material, for example, using a nano device, it will show up new features in the spectrum, which is, if you analyze it, can again provide interesting quantification of properties.
Other questions? Because what I think I see as interesting is that a lot of time we do transient and pulsed, and we have some amplitudes. When you do the full frequency, you have a shape, so you actually have a better understanding. Sometimes we say this is coming from Peltier, this is coming from Joule, but you only work at the small enough current so that only Peltier is there. But in principle, you could also take into account Joule effect. That's what you are planning to do, correct?
Yeah. Yeah, we can also, in principle, all the measurements I've shown are done at oscillating around 0 amps or 0 volts. But we can also, for example, under operating conditions, we apply maybe 0.1 amp to the system, So the system is provided our current, and then we can oscillate around this 1 amp as well. So we can track the properties of the system under these operating conditions. So this is also possible, and if we do this, we of course need to take into account your effect, which now the currents are large, so it will show some contributions.
How does the accuracy works when like the Seebeck of the material is small? Because I feel that this sativa should be something comparable to IR in your voltage, so you can get an accurate Seebeck. Otherwise, the Seebeck would be like inaccurate.
That's actually a good question. So basically, in your whole impedance curve, there is a series resistance, and the rest of it comes from delta T. So this method works well for material that have reasonable ZT. If ZT is, I don't know, 0.1 or something, you don't get enough delta T, so that could be.
There is, when you go to lower performance materials, your resistance becomes smaller. So now we are working in the milliohm range, and this is difficult to measure in some equipments. But you can gain accuracy by changing the geometric properties. For example, if you increase the length of your material, your resistance will become larger. And also, if you reduce the area, you will probably transfer from a few milliohms into 6-7 milliohms, so you are able to measure it. So you need to play a little bit with the geometry of the sample to try to get good thermoelectric response.
So you showed load plots as well. Is there any information that you get from those?
But usually, the reason I work mostly on complex plots is because it's more sensible. So you easily see all the trends. In body plots, usually this is more difficult to identify. So body plots, in principle, is like an S shape. So you have constant, a drop, and another constant. So you only see the difference between this point and this point mainly. For example, this trend is difficult to see in body plots.
The frequency at which it changes doesn't matter, or is that correct?
Yeah, usually you can track as well the characteristic frequency. So you will see, for example, the characteristic frequency here. You will see a drop around this frequency. So yeah, you can also track in body plots the characteristic frequency. This is more or less clearly distinguished.
So onboard devices that could be characterized is OMIC devices. I mean, you can't characterize gain junction, right?
You can characterize any electrical device, really, because you apply voltage, you record currents. If you have a device,
It should be linear.
But your current amplitude is
very small, yeah.
Linear.
You are always in a kind of linear regime, so you can characterize nearly any device. That's why it's very powerful, and it's been applied in a lot of ranges.
I'm asking this because you said that you would apply voltage like 10 millivolts. So I mean, if it's P in the junction, if it's not, you need the linearity, but also you need to get the device on.
But I guess the reply was that you can apply a DC and on top of it apply a small. So you can make it on.
But in DC, then the usually thing will be like.
But you're measuring is the variation along on top of that. You don't measure the DC.
Yeah. For example, in solar cells, you have your IV curve, which is nearly a diode. So usually to characterize solar cells, you fix a voltage, doesn't matter in which point of the curve, and then you oscillate around this voltage. And you identify different spectrum shapes and all different voltages. So it's possible to look at any operating condition.
Okay, if there's no other questions, let's thank for here once more.